so today's lecture is about two things that I think are kind of fun. One is, how do you make a image out of a bunch of subcomponent images? We kind of talked about this problem initially last time in the sense of, if I have a single source and a single target, we talked about how we could do multi-resolution blending, and we talked about how we could do this Poisson image editing in order to plot the source pixels into the target, right? Today what I want to talk about is kind of extending that idea to what happens if we want to put multiple sources into the same target. Or maybe there's not even really a target to do. Suppose we just want to merge a bunch of images and we're choosing some pixels from one, some pixels for the other. And also I want to bring in some of the idea from the matting idea, whereas still to make the composite last time, we needed to have the user draw this boundary around the object that they wanted to composite. What if we just let the user scribble loosely on the objects and said, okay, I want this stuff more or less, I want this stuff, I don't want that stuff. So kind of a very easy interface for the user. That's what we're going to talk about first, is this kind of multi-image compositing, and that algorithm is based on the same kind of graph cut idea that we talked about for matting. The second thing I want to talk about is the idea of image inpainting, which is basically, how do I take regions of the image? We're going to start off with thin regions, like might be caused by wires holding somebody up, and fill in plausible background where the foreground used to be. So in some sense, that's kind of like an image editing problem where we don't know what the background should be. We just know that we don't want this foreground, right? And we'll talk about that for kind of increasingly complicated regions. Okay, so the first idea is basically what I would call graph cut compositing. And so the clever idea of this whole approach is, we talked about this, we alluded to this at the very end of the last lecture, which was, the user's chosen boundary may not be so great for making the most unobtrusive match between the source and the target. Why don't we make an algorithm that finds the best boundary, right? And so what we're going to do is say, okay, what if there was no blending at all? What if I said, okay, I want to find, given that these pixels have to come from the source and they have to go onto this image, find me the subset of source pixels that I should put into the target in exactly the same place in a way that is going to be as unobtrusive as possible, right? So kind of the idea is that, to make it very simple, let's suppose that I want to put two images together at the middle, right? So it's like saying, okay, here is, so this is kind of like the effect they used to do in TV shows and movies where they wanted somebody to be playing their own twin, but they only had one actor and they didn't want to hire twins, right? So how do you do that? Well, you have one plate where you've got person A who is like talking to each other, or talking to an empty place, right? And then you've got another plate shot in the same set with person B that is actually the same person taken at a different time. And the idea is I want to build an image that looks like these people are talking to each other in the same scene. This is high quality drawing here. And so how does this work? Basically, that's like saying the user says, okay, these pixels here have to come from this left-hand image. These pixels here have to come from this right-hand image. And algorithm, you go find a way to draw a dividing line that stitches these two images together in as unobtrusive of a way as possible, right? So that's what the problem here is going to be, is finding the line that divides these two images so that when I put them together at the seam, the result is as imperceptible as we can make it. Okay, and I believe I have a better picture of this here, right? So this is kind of like the nicer version of that picture. And so this is very similar to the kinds of constraints that we put on the matting problem, right? Where we said, okay, the user scribbles and says, this stuff is definitely foreground, this stuff is definitely background. And we talked about the way that grab cut, for example, which you implemented on the first homework, uses those constraints to find the best segmentation between the foreground and the background. In some sense, this is kind of the same problem. We're going to kind of, in the context of compositing, I like to call this a seam, right? So a seam is basically, I guess you can't see this, a seam is like the division between two different images that we're putting together, okay? And so the idea is going to be the same. Let's suppose that I kind of take my picture here and I turn into a graph, okay? So again, the setup is going to be very similar to the graph problem that we showed before. This time I'm going to be smarter and not draw so many nodes. Okay, and again, I'm going to define two terminals, which I'm going to call kind of source and target. Now, this is okay for the moment, but we're going to generalize this to the idea where there's really not one image that is playing the role of the source and one that's playing the target. In some sense, as we go forward here, we're going to treat all these images basically equally, and it's just a question of which pixels come from which. So the idea here is, okay, so maybe initially all these pixels could be either connected to the source or the target, but the user says, okay, you know, these 3 pixels I absolutely have to connect to the source side, and maybe these 3 pixels I absolutely have to connect to the target side. And then these other pixels maybe are connected to both the source and the target initially. But what I want to do is I want to do the exact same idea with graph cuts, where I want to now cut links in this graph that completely sever the pixels that go with the source from the pixels that go with the target, right? And in the very same idea, what we want to do is we want to find a cut that has the minimum cost to separate the source pixels from the target pixels, okay? And so again, what we need to do is we need to define weights between these adjacent nodes that tell the graph cut what is advantageous to cut and what is not, right? And so again, the intuition should be that, you know, I want it to be, so here's, you know, there are different ways you can think of making the cut. So let me show you this picture for a second. So this is kind of the picture, right, that I just drew in an albeit more polished way. And so what I need to do is I need to figure out what are the weights between the edges. So how to assign weights. So again, basically the idea is that, pull my page over here. So the idea is that the cost of cutting an edge should be low if basically the source and target pixels have similar colors on either side of the seam. Right? What that kind of means is that if I were to draw the line between those 2 pixels, since pixels I and j in the source look basically like pixels I and j in the target, that if I take I from one and j from the other, I'm not going to introduce some weird edge that wasn't there in either the source or the target, right? So one way of doing this is to say that the weight between adjacent pixels should be something like this. You know, the source at pixel I minus the target at pixel I plus the source at pixel j minus the target at pixel j. So this is a very simple way to do it, where I basically am saying, okay, you know, pixels I and j are on either side of a hypothetical boundary, right? And what I'm saying is that in both the source and the target, I want, you know, these, you know, 1 by 2 blocks of pixels to be pretty similar. And that way, if I draw a line between I and j here, I'm not really introducing a lot of energy, right? So does that make sense? Yeah, question.
Will this work for natural images?
Yes. Yeah. So we're gonna show a bunch of examples where this works. Okay. Yeah. Why do you ask if it works for natural images?
If background has the same color.
Yeah. So places where the background has the same color, you know, in some sense, that's kind of what you would try to do, right? So if you imagine that I wanted to make myself talking to myself over a white background, in some sense, I could be able to draw the seam anywhere along this white background, and in theory, I should be able to sandwich those pictures together. You wouldn't be able to tell if there was any difference, right? So cutting through broad, featureless regions that are the same in both the target and the source are good choices, right? Other questions? So another thing that I could do is, well, okay, so let me just also say that if pixel is scribbled in S, then basically I should say that the weight from that pixel to the source is infinity, and the weight from that pixel to the target is 0, and vice versa, right? So again, the user scribbles to guide the algorithm, and those scribbles basically say, okay, look, these pixels are infinitely expensive to cut, so the graph cut will never pass through them. I will always sever those pixels from the opposite terminal, right? And if I recall correctly, basically, I don't really do anything for pixels that are not stroked, right? I let the algorithm figure out how to cut the edges in order to do the best job, okay? So kind of unlike matting, there's no kind of notion of prior probability of non-stroked pixels being part of the source of the target. We don't try to learn anything about those unstroked pixels, okay? So this is one way, and so kind of the result is that, this implication is that seam passes through kind of, I mean, there's nothing that says that these colors themselves have to be exactly the same, right? So for example, this pixel could be black and this pixel could be white, and the same over here, and this cost would still be low. And that's okay, right? All we want is that seam passes through, edges. Well, edges is probably not the right word. Seam passes through regions that will be kind of imperceptible. This is a poor hyphenation. Imperceptible. Okay. And so let me just show you a picture of how this works. So I believe I have this as a PDF and not a picture of MATLAB. So here is my example. So again, back to cows. And so here is one picture of a field of cows, and here's another picture of a field of cows, right? So what I want to do is I want to say, okay, I want to take these cows and put them in the other picture, right? And this is the most amount of work that I'm willing to put in. I just want to scribble roughly on the surface of these cows and say, okay, hey, cow in the foreground and cow in the background, go over there. And so if I do that, this is the result of running this graph cut segmentation algorithm. So basically now, after I run the segmentation algorithm, every pixel belongs to either the foreground or the background, and the boundary between black and white is chosen in such a way that I minimize the cost of cutting all those edges, right? And the result looks like this. And I mean, it looks pretty good, actually. I mean, you might notice that actually this cow is actually the same cow over here taken a few minutes later, and so that might throw you off a little bit. But in general, I mean, there's nothing visually wrong with this picture that wouldn't lead you to believe that this wasn't actually taken, in terms of, again, all this being said is that you have to be very careful to do a good job matching the lighting and matching the shadows and so on. Otherwise, it will look very strange. But I mean, this looks pretty good, right? Question? Okay. No?
Yeah, so in the weighting between pixels.
Yeah.
You don't actually look at, because it looks like you're, oh no, you did never.
Okay.
Okay.
So,
I read that wrong.
okay, good. So let's make this, so let me just say, okay, so this works pretty well, and it actually works surprisingly well. One other option for the weights is another possibility for weights is something like the following, where I have the same kind of numerator. So I'm going to put that up here. And in the denominator, what I'm going to put is basically something that involves the gradient of these things at every pixel. And I didn't really allow myself so much space here. So here, D is basically the direction of vector pointing from I to J. So what this is basically saying is that if the gradient is large, right? So basically, this is like saying that, let me make sure I got this right. So if the gradient is large, that means that there are edges happening in the image along the same direction as where I want to cut. And that means that if this denominator is large, then the weight will be small, and that will be an appealing place to cut. And so the idea is that this prefers kind of edgy regions of the image to make the cut. So the idea here is that what I could do is I could disguise my seam somewhere in the background where it's really busy, right? So if you imagine that I've got some foliage or some trees or something like that where there's already a lot of pixel variation, in that case, that would be a great place to hide the seam because there's already so much noise there that you wouldn't notice that there was additional weird stuff being introduced by the seam, right? So in some sense, it's kind of counter what I told you about putting the seam through a flat white surface. In some sense, both of those things are viable strategies for drawing the seam, right? It's just a different choice of energy function, and what you could do is swap out different weights in your graph cut and see which one you like the result of better. And after having talked to people who do this for a living, they don't necessarily have a hard and fast rule for where they draw these lines to butt up different video sequences together. And in some cases, they'll go through a smooth region, and in some cases, they'll go through a busy region, and even that may be happening in the very same image, right? There may be a scene that really jumps around in the image. So again, taking a look at the interviews that are in the back of the chapter talks a little bit with artists about how they really solve this problem. It's kind of interesting, right? So again, this problem is probably not really solved, I would guess, automatically in the industry, although this, I think, is approaching something that could be solved automatically, and maybe some packages are starting to include it, but a lot of it is still done by kind of careful manual drawing of what will make sense. Okay. So what's really an interesting extension of this is that, we could now extend this to cases where I have more than one image, right? And you can imagine that I could say, okay, I want to scribble on some stuff from image 1, some stuff from image 2, some stuff from image 3, and make me a multi-image composite. And so what I'm going to do for you now is kind of an example of that. And maybe you remember a couple of years ago there was a commercial for Microsoft where it was like a woman who was trying to get her family together for a picture, and in every single picture, someone looks weird, but she does this magic Microsoft product, and suddenly they're all looking forward and smiling, right? And that's exactly something that came out of a SIGGRAPH paper, which is the one I'm going to tell you about now. And I can actually demonstrate this for you here, and it's pretty neat to watch. And so the idea is that extension or generalization to multiple images. And so kind of the canonical example of this is like the kind of family portrait idea, right? I want to make the family portrait where everyone is smiling. And so, again, in this case, I may have a whole bunch of images, none of which is really playing the role of source and target explicitly. It's kind of like saying, okay, I want this person from here, and this person from here, and this person from here, and this person from here. And then these all go into some algorithm, and the result is something where I have kind of multiple seams. You might imagine it kind of looks like some kind of paint by numbers thing where, in different regions of the image, I'm taking different pixels, right? So the good news is that this can be done. The bad news is that it can't quite be done directly with graph cuts in the same way. And the reason for that is that graph cuts is set up where I only am labeling a pixel as basically source or target, 0 or 1, right? There is no immediate, like, multi-label graph cuts where I'm taking this graph and connecting them to multiple terminals at the same time, okay? So instead, to approach that kind of problem, what you do is you go through this kind of an iterative process. And so basically, I can't immediately apply graph cuts because this requires only 2 terminals. So instead what I do is something where I do a series of binary graph cuts problems to get to what I want. And so, for example, let's suppose that I have a initial labeling of pixels in the composite that looks like this, okay? And so what I might do is I might solve a problem now where I cycle through a problem of saying, you know, I've got my graph. And these guys are connected to 2 terminals, and those terminals are named, you know, flip to 1 or keep current label. And that way what happens is that the only thing that can happen at this stage is that some of the pixels that were not labeled 1 before might be able to flip to 1, right? So maybe at the end of this, I might get something that looks like, you know, this. So the 1 region has expanded into, you know, what used to be labeled as something else. And then I solve another problem where I change the flipping label. So now the 2 terminals are like flip to 2 and keep my label. And at the end of that process, maybe the image looks like, you know, something weird like this, where now 2 is expanded to here and here. I guess I can't really do it like this, so maybe I still have to have something like this. So again, the only thing that can happen is that 2 grows, right? And so the idea is I keep on iterating this process with each of the labels in sequence, and I keep on doing that until I don't make any more flips, right? And so what you do is you kind of define this cost function that reflects the overall cost of the labeling, but I have to get at that minimization of that cost function by this sequence of binary problems. And this process is called alpha expansion. Which I nicely spelled wrong here. Alpha, well, I mean, I spelled it weirdly. This alpha is not related to alpha from alpha maths, unfortunately. So it turns out that, you know, one nice thing that I didn't really mention for graph cuts is that, you know, graph cuts for binary labels has this great guarantee that you'll get the minimum cost labeling. Alpha expansion, you don't quite have the same guarantees, and you don't necessarily know how long it will take, but in practice it's very fast. I mean, it's almost as fast as normal graph cuts. And so that's exactly the problem that we're going to study, or that's actually the process that we're going to use for the multi-image case. And so here is an example from your predecessors in my class. So here we have 3 images of the class making goofy faces, right? And so what I want to do is I want to make a nice family portrait of these 3 people, okay? And so to do that, and this is one of the things I'm asking you to do on the homework, I'm going to use this program that has helpfully been released for you by the original authors. This is the work of Agarwala and all. And so what I'm going to do is I'm going to make a new composite. The way that this works is I'm first going to choose one image that I'm going to kind of choose as my nominal target, right? So you just click on one of the images that you have. So this is an image that's not bad because everyone looks pretty good except for a few weird people. And then I'm going to load stack, which means take all the other images that I want to try and composite into this, okay? And that gives me another window. And so then what's happening is I'm going to basically be working back and forth between one of the sources and the composite. And the interface of this is extremely simple. So actually I have my little pen here. So what I'm going to do is I'm going to say, first of all, let's take a look at this guy over here on the right. You're not looking face forward, right? So let's see if we can find an image over here where he's looking okay. So here, this guy looks pretty good over here. And so all I have to do is scribble on his face And you'll see that in the composite, his head clicks over to be right. His neck is still not maybe 100% right, like his shoulders look a little weird. So I could just kind of scribble a little bit more and even him out. You can see I have to get his arm here, right? So now he looks pretty good. Maybe a little bit of, yeah, that looks all right. These guys on the right all look okay. I mean, this guy here could maybe be taken over, you know. I need to scribble on his, yep, so now he looks pretty good. This guy over here in the middle, let me see about taking his head. Okay, so now I can see that, you know, his shoulders are kind of messed up. So I need to take some more over here. So yeah, here I need to be a little bit, you know, careful. Here now I'm getting into this guy's hair, which I've screwed up a little bit, but maybe not too obviously. And so let me just scribble a little bit more here. You know, so now things are looking pretty good. Maybe I need to make the lines of his shirt line up a little bit better. Again, I'm not spending a lot of time on this. So at this point, you know, oh, I took this guy's nose by mistake. Uh-oh. So I have to go back and get this guy's nose back in. So here I just say, okay, you know, no, for this guy, I need to get this part of his head, right? This for sure needs to be here. So let's look at, like, this woman over here. I like her head, but I don't like her arms. Like, she's moving her arms, and then let's see if there's a better picture. So here she's got better arms, but silly face, right? But all I'm going to do is I'm just going to scribble and say, you know, take these arms over here. And now she's got one arm that looks good and one arm that looks bad. So let me just scribble over here. And something is up over here, right? And finally, let's see, there's this guy in the back. I guess he looks the best over here too, so let's take him. Got to get his whole head, right? And so now if I look at my composite, you know, looks pretty good, right? And this was, you know, being done on the fly, right? So, I mean, these are not like super small images. They're probably like, you know, a few hundred, 700 pixels wide or something like that. So your task for part of the homework is to do a similar portrait with your friends where you ask them to make goofy faces and then try and put them together. Or something, it doesn't have to be your friends, it could be something else, right? I mean, originally in my book I had this kind of boring example with like plants and stuff that were rearranged. It's like, my friend looked at this book and said, what a dumb example this is. So then I did it with my class, and it's a much more engaging thing. Yeah, so this is basically, under the hood, this graph cuts algorithm using alpha expansion to assign multiple labels. And actually, at the end of this, then, I should be able to see a picture that shows here, basically, these are the color-coded labels of what actually got taken from one image and put into the composite, right? So basically, almost all of the image turned out to be from the original red image, but I chose, you know, the head and the arms of this woman and the head of this guy from the green image, and I chose these heads and this head from the blue image, and actually this guy's arm came from the red image. So you can kind of see that this is the resulting choice, and these were the original strokes that I used to get there, right? And so you can see this is much less laborious than kind of manually trying to make outlines of what you want. You just kind of, you know, it's super fast, right? Super easy. So again, this work was originally called Photomontage, and it was done by Agarwala et al. So what I'm asking you to do in the homework is basically the same thing, and you can also show me the strokes that you used and the resulting labeling. Okay, so any questions about that? And again, you can use kind of similar techniques to do things like if you go out on a, you know, so another application of this is that when you make a panorama from multiple images that you take on vacation, for example, so your camera probably has a panorama mode where you take a bunch of images and it gets stitched back together, you know, one option for that stitching is literally just to draw a seam between things. Certainly that's a good thing for if you're, for example, if you're filming in an environment and you need to get rid of this pedestrian that walked past your shot, you could just kind of graph cut out that person and say, okay, take the background from this other shot and put it in here. Another thing that you can use that's kind of neat is that, again, instead of like kind of scribbling to take particular regions out of the image, you could also do something that's kind of more like literally paint by numbers, where you say, okay, you know, up here I just paint strokes and I say this is sky, right? So now go to a big image database of images with labeled sky and find me the best sky that minimizes my graph cut objective. You know, so I can basically do like on the fly sky, ground, you know, pedestrians, right? And all that stuff can be drawn from not just a single image to characterize each texture, but multiple images that are all being searched to find the best, you know, the lowest cost composite of putting those seams together, right? Okay, so any questions about this? All right, so let me just go back to my PowerPoint, because I believe I have, you know, this is, whoops, not this. So this is basically just the result. I guess this is the example I did for my book. So here I apparently did a little bit more scribbling than I did in the original, but it looks basically the same. I was a little bit more careful with this one, I guess. And this is just a picture of what those intermediate alpha expansion problems look like. The details of exactly how you set up the alpha expansion problem are a little bit tedious in the sense that I actually introduce a couple of extra nodes, these white dots, in the problem at every step. Basically, those white dots are introduced between pixels that originally had different labels. And so, again, it's not hard to set up these intermediate problems, but there is a little bit of, you know, just machinery to do it. And so all the details of how you actually set up the alpha expansion problem are in the appendix of the book. Okay, so the next problem I want to talk about is called image inpainting. And so I'm going to close these guys and go back over to here. Okay. So inpainting is a word that actually comes from the kind of art history world, where conservators of paintings had to deal with things like cracks and scratches in original paintings, and they needed to restore them to make them look as nice as possible, right? And so, again, they have to be extremely careful to make sure that the restored painting is as true to possible as the original painting, and that the changes that they make are as imperceptible as possible while being consistent with the original paint strokes, right? And so there are a couple of approaches to this. One that is kind of you know, the original approach that was really actually inspired by talking to art historians and understanding how they actually do this restoration. And the other one is a little bit more of a computer graphics-y kind of approach, where it's much more kind of opportunistic, data-driven, not as, you know, artistically minded, but also can still produce some good results. Let me just say that, oh, and so, you know, when you see something like the, you know, a function in Photoshop that has something to do with like clone brush or something like this, where you're doing something where you're trying to take texture from one image and fill it in the image. Or you basically, you know, one thing that Photoshop might let you do is say, okay, you know, there's this, you know, there's this person in a field of flowers. I want to erase the person and put flowers in the middle, right? That kind of texture cloning of filling in the middle with reasonable looking texture is basically the same kinds of algorithms I'm talking about here. So all this kind of texture synthesis stuff that you see, you know, for cloning brushes and stuff like that is really the same stuff I'm going to talk about right now under the hood. Okay, so so the original idea was looking at basically very thin kind of holes, right? So, you know, if I have a piece of art and it's damaged, right, you know, there's probably going to be some sort of a thin crack across here or a scratch or something like that. And so, or another case where this comes up a lot is something like a scratch on a piece of film, right? So it's very common when you're filming with a camera, you know, analog camera that has moving parts, right, that some piece of metal or something kind of makes contact with the film surface and leaves a scratch, right? So if you look at old movies, you see all these scratches, and of course, if you apply the old movie effect in After Effects to video, you get these kind of mock scratches that are supposed to mimic the film having gotten scratched up over time, right? So basically, this is like the restoration of such scratches. And, you know, actually, this still comes up. And again, if you look at the back of the book, you know, I talked to some people who actually worked on these for not only Hollywood films, but also for example, they recently restored the Apollo moon landing, and that video was kind of beat up, and so they had to make it look as good as possible, again, without really feeling like you're changing the original pixels of the image, right? So the idea is pretty simple conceptually. So here, the idea is we have a concept called an isophote. And so isophotes, basically what that means, so iso means same and phote means color, more or less, right? And so what this means is that we are kind of looking at regions of the image where the color is the same, right? And so what I want to do is I want to, if the color is the same going to a certain region, I want to keep on pushing that color into the region in the directions where everything is being equal, right? And so the idea originally is to propagate isophotes into holes or inpainting regions. So I guess in this section I'm going to kind of slangily call the thing, the missing pixels, I'm going to call them the hole, okay? And so we know that if I have an image, right, that say it's black on one side and white on the other. So if I take the gradient of the image, right, the gradient basically points in the direction at a pixel where there's the greatest change, right? So for example, at this pixel, the gradient is pointing perpendicular to the edge. And so this is basically the gradient of the image at x. And so what I really care about is places where things are not changing, right? The direction in which the image is changing the least is perpendicular to the gradient. And so this direction here is like the perpendicular direction to the gradient at x, okay? And so the original inpainting approach, which is proposed by Bertalmio et al., was to push the, basically, it is to make sure that the edges of the image are not changing in the direction of the isophotes. And so basically the edges of the image, kind of what we talked about last time, we can represent by the Laplacian of the image, right? So this is like one filter that I could run across the image and produce an edge map, kind of. This is kind of like saying, how strong is the edge map? And so what I want to do is I want to find where these edges are strongest, and I want to push them along the isophote directions into the hole, right? So kind of the idea is I want to continue edges into the hole, right? And so a mathematical way of saying that is that and this is where it gets a little bit hairy. So here, this delta basically means the change in the Laplacian dotted with the isophote directions should be 0. So let me write that down. So this is like saying the change in the Laplacian, that is image edges, and this is along the isophote directions, should be 0. Right? So I want to basically say that, edges kind of continue along directions that have the same intensity going into the hole. And so one way that I can make this work, right, so again, not all of you have probably had partial differential equations, but when I have a system like this, what I can do is solve it iteratively, meaning that I can basically make a inpainted image that I continually update over time. And so the way I would do that update would be something like this, where I'd say the partial of the image with respect to time is equal to this thing. So why does this work? This is like saying, well, when this thing is 0, then di dt is 0. That means that the image has stopped changing, right? So in some sense, everything stops when the right-hand side of the image, when the right-hand side of the equation is 0, which is what I want, right? That's kind of like saying that I've satisfied the conditions that I want for inpainting. In practice, to make this work, you need to like discretize everything, and you know, you need to make it work with a digital image, right? This is a very continuous-looking thing. So this is kind of like the equivalent of saying that if I had, this is more like almost like a fluid dynamics thing, where if I had a continuous fluid and I, you know, wanted to fill in the hole, what would I do? I would push the fluid in a certain way. And so to illustrate kind of how this works, let me just show you a picture. So this is kind of like a picture saying, you know, again, what am I trying to do? So this, actually, I probably should have shown you this at the beginning. What I want to do is I want to push texture, you know, I want to propagate things along isophote directions. What I mean by that is that I don't want to push it, like in this picture, in the direction of the boundary. So this here is like the unknown region, the hole, and this stripy region is what I know, right? So one thing you could argue is, well, why not just push like an onion peel directly into the stripy region, like perpendicular to the stripy region? Well, if I do that, and I just kind of push the intensities along, I end up kind of corrupting what I actually should see, right? What I want to do is I want to push this here into the hole, basically right along the direction that everything is flowing, right? So I want to keep on pushing stuff this way. And that's what the, you know, the perpendicular to the gradient is. That's saying this is the direction in which you should be pushing the new intensity, and what you should be pushing is the edges, right? And so this is like kind of a sketch of schematically continuing the edges into the hole along the direction that they're going, right? And so here's kind of an application of that. So this is a ski lodge in Turkey that I was at in the winter, in the summer. And so one thing that kind of mimics what you might do if you're trying to do a visual effects shot is you want to remove the wires of the ski lift, right? So I want to remove these black wires. And so you can imagine that this shouldn't be too hard. All I want to do is I want to push the colors from either side of the wire into that region in a convincing way. And so here is kind of like my drawing of I want to remove this stuff. This is just a binary mask that tells the algorithm where the hole is. And then I start running the algorithm for multiple iterations. And so in the bottom right-hand corner, I have the number of iterations I've done. And so here you can see that the wires are still visible. I mean, they look kind of like smudgy, right? And so this is actually kind of similar to what you read in the interview section as what someone called the glass rod effect, right? So it's like, it looks like, yes, I have removed the blackness of the wire, but it's somehow blurry or fuzzy. I can tell something is wrong there. But as I keep on iterating, the wires slowly go away until at 10,000 iterations, if I showed you this image, you probably would not have ever thought that there were wires in the image, right? I mean, it looks pretty good. And even, I mean, of course, from your distance, it looks fine. From my distance looking at my computer monitor, it still looks good, right? So this kind of thing works pretty well for very narrow, very small holes, right? Places where there's not that much ground to cover between the existing pixels that I want to keep and the stuff I want to replace. On the other hand, this doesn't work so well when I have a big hole to replace, right? So for example, here, let's suppose I go back to my ski lodge and now I want to remove these buildings, right? So say I want to remove this building in the middle of the grass. Well, you might say, okay, well, maybe that will work okay. If I do that, here is the mask again of what I want to remove. Here's 20,000 iterations. Here's 2 million iterations. And I can tell you it doesn't get much better than this after I keep on iterating, right? So here, there's still this smudginess inside the hole. Like, it's definitely visible in both of these places. You'd never accept this as something that wasn't untampered with, right? And so part of the reason for that is that these partial differential equation-based algorithms, they are assuming that everything is kind of smooth, pretty smooth. And so you don't have the ability to recreate convincing texture inside the hole, which is really what you need to do here, right? So here, I need to be reproducing nice, detailed grass texture inside that hole, and this kind of mooshing of the intensities from the outside is never going to give me that, right? No matter how many iterations I run, it's always going to look pretty empty, right? So in my opinion, the approach I just told you about is pretty limited to very, very tiny scratches, very, very narrow holes. And actually, this is the result of doing this inpainting. This picture here is the result of just taking the Poisson algorithm we talked about last time. What I could do is I could say, okay, the ski lodge image is the target, and the source gradients that I want to put in there are 0, right? That's kind of like the equivalent of saying, okay, keep the target colors at the boundary and try and get 0 gradients inside the hole. Basically make the hole as smooth as possible and find me like a nice, smooth interpolating function between all the colors on the boundary. If I do that with Poisson, I get this picture, which in my opinion doesn't really look that much different than doing this more complicated PDE, right? And the idea is the same, is that, fundamentally, I'm still solving this differential equation that just, it's too smooth. It doesn't really ever create texture, right? So to create texture, like you see in Photoshop for texture synthesis, we need something that's a very different algorithm. Okay? So let me pause and ask for a second. Any questions on the first part? Okay, so the second part is much easier to understand how it works, okay? So the second part is very procedural. So the idea here is, okay, I've got a region that I need to fill in. That's what this omega region here is, stripy region. And then what I want to do is I want to slowly chip away, taking blocks of the image from the outside and just taking a block of pixels from somewhere else in the image and sticking it into the hole, right? And so here you can see that kind of what I've done is I've taken this block of pixels that's labeled psi sub q, and I have identified this as a good match, and I've stuck it into here. And the way I've identified it as a good match, which I'll talk about in a second, is that the part of the image that occurs, so here it's like saying, okay, here's this block I need to fill in. I know some stuff on the left that exists in the image, and I try and find the best block in the image that has a complete block to fill in the part in the right. And so it's kind of like saying I just steal the best block I can and stick it in. And the inpainting process basically chips away at the outer boundary doing that. And so really the only thing that I have to figure out for this algorithm is, number one, what is my metric for what makes two blocks a good match, which, as we can see, could be just as simple as the sum of squares distance. The other question is, what order should I fill in these blocks around the boundary, right? Like, why did I choose this region here first instead of, this region over here, right? And so the idea there is we have to devise what's called a priority function to choose at any given state of the algorithm what's the next thing I should try to fill in, okay? And so let's go back to my slides. So I would call this basically patch-based inpainting. And really the canonical algorithm for this was proposed by someone called Criminisi. Okay, so I already kind of told you in words the basic idea, but here it is as a kind of a pseudocode. So basically, I have my hole I'm going to call omega. And the first step is basically determine a priority, let's call it P of P, for every pixel on the boundary, right? So that little symbol here means boundary of. Okay, and so now I take the highest priority pixel, let me call that P hat, and make a patch around it. This is typically some square patch, maybe like 9 by 9 patch. You can set the size of this patch around it. So that means that what I have is, I've got some part of this patch that is inside omega, and then I've got some part of this patch that is the original image, okay? And so I can call this my psi sub p hat, right? This is the best patch I found along the boundary. And then I can find the best match psi sub q hat outside of omega, basically a full W by W patch. And then I basically copy the pixels corresponding to the hole in the patch on the boundary from the patch that I found that matches up the best, right? And then I have to do some bookkeeping. I have to shrink my unknown region, and I have to update my priorities, right? So now once I've done this, once I've copied these pixels in, the region has gotten smaller, the inpainting region, and I have some new boundaries on the part of the, so I basically introduced some new boundary parts on the whole, right? And so I think that the most important thing here, so basically I've already answered almost all these questions. It should be pretty clear how to do the copying. Find the best match could just be as simple as the sum of squares differences between the colors in the P and the Q patches over the region where the hole is not existing, right? So really the only question here is, how do I define the priority of pixels that I should do? And so Criminisi called that the fill front, right? The idea is, how do I know on this fill, well, I guess the fill front is the entire boundary. How do I choose the best pixel on the fill front to start pushing the color in, right? And so let's look at this picture here, right? So here are some possibly good, possible pixels to consider. Okay, so basically the priority term that was proposed in this paper was composed of two parts. One was called the confidence term, and it only had to do with the shape of the hole. It didn't have anything to do with the colors in the image. The other one was called the data term, which conversely just had to do with the data in the image, basically. And so let's look at this over here on the left, which kind of illustrates the confidence term. So all things being equal, it seems like the smartest thing to do would be to say, okay, pixel B, right? So if I were to draw a box around pixel B, would that be a good place to start shoving in some new colors? Probably not, right? Because it's kind of like this little, there's like a peninsula of known colors sticking into the unknown region, but most of the pixels in this region are unknown, right? So I could have a big chance of putting stuff in there that would not make any sense. Whereas pixel A over here is like a peninsula that is a peninsula of unknown stuff jutting into a lot of known stuff, right? So pixel A should be a very appealing candidate because almost all of the pixels around it are already known, right? So in some sense, long, thin tendrils that are sticking out into known space are the most natural things to kind of chew away first because I know all the stuff around it, right? And then, pixels that are kind of like, on basically almost like a flat-sided region, those are just like, I know half the pixels, I know, I don't know half the pixels. And so you can imagine that a very simple way of talking about this is just like the percentage of pixels in the neighborhood of that boundary point that are known, right? It's a little bit more complicated than that, but that's kind of the basic premise, right? I should be filling in things where I'm confident about the surroundings, okay? So initially, what you could do is you could say that all the pixels in the known region have confidence 1, all the pixels in the unknown region have confidence 0, and what I do to figure out my confidence on a given point on the boundary is I basically sum up all the confidences of the known pixels where I'm at. Or, yeah, so I guess since all the confidences inside the boundary are 0, that's like saying just add up all the confidences in my region, right? And so that kind of prefers pixels like A that are sticking out into places. But at the same time, there's also this consideration that kind of comes back from the original inpainting algorithm that we talked about first, which is that I also want to prioritize pushing strong edges into the inpainting region early, right? Because a big problem would be that you don't want to have edges that kind of, don't come together in the middle, or kind of, even worse, kind of just vanish at the boundary of the hole, right? What I want to do first, and this was an important observation, is I want to push in along places like this point. So let's look over here in the second figure. So here, the idea is I look at the texture of the image, and I look at the gradient, and I look at kind of the perpendicular to the hole boundary, right? And so the best possible scenario is something like where this pixel P is labeled here, or where this pixel is labeled here, where not only is there a strong gradient in the background, but it's also coming right perpendicular to the hole boundary, right? That's a candidate for pushing on into the hole boundary. Push that edge in there first, right? So this pixel up here that looked appealing before because it was this peninsula is not really appealing from a image painting point of view because really there's nothing edgy locally about this pixel, right? And here, yes, this pixel is on the edge with respect to the image gradient, right? So there's a strong gradient of the image here, but that gradient is not pushing into the hole, right? It's kind of almost parallel to the hole, right? So this pixel P and this pixel over here are actually much stronger candidates for the data term, right? And so if I were to write that down, basically the priority P is basically the sum of what we call a confidence term, C of P, and a data term, call it D of P. And so the confidence term is nothing more than the sum for all of the pixels in the window around P of the confidences of those pixels. And so basically, known pixel has C of P of 1, and unknown pixel has CP of 0. Okay. And I guess if I wanted to, I could, divide this by the number of pixels. Since that's the same for everybody, it doesn't really matter too much. And the data term basically says what I want is that the absolute value of the normal. So this is basically the normal to the whole boundary, right? That's like perpendicular to the whole boundary. That vector dotted with the basically, this is the data term perpendicular to the gradient. Let me just make a... So what this is saying is that, this is perpendicular to the gradient, and this is the magnitude of the gradient. So what I want to do is I want to find high gradient regions, right? Places where there are edges. And I also want the gradient and the whole boundary to be perpendicular to each other, right? I want to make sure that the whole boundary and the gradient are, so the gradient is basically pushing perpendicularly directly into the hole, right? And I mean to make sure I have this term so that, you could take the gradient of anything, right? You could take the gradient of noise, and if that, you could, even a flat region will have some direction to its gradient. And I don't want to just use some, some gradient of some flat region that coincidentally lines up with the normal to the whole. I need to make sure that the gradient is actually strong there. That's why I need this extra term. Okay. So that's basically about it. So basically, all I do is at every step, reevaluate the confidence in the data term for every pixel along the whole front. And then I find the one that looks the best. I bring some other block from the image in, and I plop it into that pixel, right? And in that way, the texture of the inpainted region will always look pretty good, right? Because I'm actually copying textures that existed in the original image, so I'm not losing any detail. There's not going to be any smudging of the image in this kind of algorithm, right? Okay, so let me pause and ask. So any questions about the general idea? So let me just show you some examples that will hopefully make it more concrete. So here's an example of an image. This is Mass Mocha, for those of you guys who've been to Mass Mocha. So what I want to do is I want to take this stuff out. I want to make it look like there was no window frame in the image, okay? And so what I can show here are a couple of iterations of chewing away the, so basically here this is maybe after a few hundred iterations of choosing little blocks that are substituting them. And you can see that what's getting shooing away first is, like for example, this strong gradient that's going through the pixel, going through the inpainting region kind of perpendicularly, right? This stuff is getting taken out first. So anything that is kind of like these trees here that are basically perpendicular to the boundary, those are also getting taken out first. And so those are the first to go, so the lines get continued through the inpainting region. After a few more iterations, I have filled in, kind of all the way through that. So now the inpainting region is no longer connected up. It's just a bunch of unknown pixels. And I keep on doing that until I chew away the image, and I get an image that looks like this. Now, if you looked at this on first glance, you probably wouldn't have too much of a problem with it, except for maybe the stuff that happened down here is a little bit weird, right? So like there's this yellow part of this pole that seems to be kind of disconnected. So if I put my mouse over that, you might look at this and say, okay, the bridge looks good. So the bridge looks good, the trees look good, right? So, a lot of this image looks pretty good. And so actually I have some animated GIFs that I made of this process for different regions. So let's see how these look here. So kind of what you're going to see is you see the initial inpainting region flash up in green, and then you see it get chewed away iteration by iteration. And so actually what I showed you was the lower right-hand triangle of this image. So you can see that in that region, things look pretty good. In the left-hand region, which is probably the reason I didn't include this figure fully in the book, things don't look as good, right? There's this weird stuff that's left over that didn't copy over, very well. The problem with this algorithm is that it's possible to make one bad choice that haunts you forever, right? So like if you fill in the wrong piece of texture somewhere, then the next step around, you're now trying to match other parts of the image with that bad texture, and bad texture can very easily propagate into the image. But for some for some places, so this is again, you can't expect a lot from an algorithm like this on a very detailed natural image. It's best when you've got something that is really more like a kind of a uniformish texture, like again, flower garden, clouds in the sky, grass on the ground. So let's look at another example. This is an example that I think actually worked pretty well of a hole in a wall. Whoops, what did I do here? So here, basically, this is a big hole, and I painted over it, and now I start to chip away at it. And again, this stone, or this is a fresco in Pompeii, has pretty, uniformish texture. And so the stuff that gets filled in, doesn't look too bad. I mean, if you had seen that image without the original, you might think, yeah, okay. There's maybe a little bit of weird, you can tell that the line here, that you feel like it should kind of be a little bit more, extensive, like that red lines which about continue across the region, and it doesn't. That may make you think twice about whether this is a real image. But again, if you think about it, that's a very faint, this is not a very strong line, right? And so there's no incentive. You can see that during this whole iteration process, this gradient is not strong enough for the inpainting algorithm to choose those pixels to push right through at that point, right? So there's nothing that connects those lines up in the middle. But, looks okay. So in the spirit of increasingly bad examples, so let's see, here's another Mass Mocha image where I'm trying to remove these supports. And again, places it looks good are places like, the edges of this corrugated shack, I think, end up looking okay. Brick texture, looks okay. But again, even here in the bricks, you can see that there were some weirdnesses around this window. Again, it's actually pretty surprising that the window got completed with a corner that didn't look too bad. I mean, again, it's probably stealing from other windows in the scene, but there's this kind of weird crud on the walls that, comes from the fact that there's kind of these maybe regular stains and spots and stuff like that, and it just took a texture sample from one of those and it put in something that didn't belong there, and then it propagated. So here's a case. Here's a case of texture, but here, this texture is, again, a little bit maybe too large scale for the size of the window that I chose. So here, I'm choosing stuff that looks kind of rocky to fill in the middle, but something is not right at the end, right? I mean, it doesn't look like these are rocks that are kind of actually, part of it looks okay, but, the middle of it doesn't look very good. And actually, this is, of course, going to be true in general, because the more you push into the middle, and the further away the middle is from the boundary of the hole, the less confidence you have about anything that you've propagated in, right? So that by the time you get into some middle region of some really big hole, all bets are off, and you could get kind of, I mean, what you'll get will still be textured, which is good, but it won't be the right thing, probably. But, you know, I mean, there's definitely nothing to complain about for big regions of this, right? So if you look at kind of like this starfish arm here, the stuff that gets put behind the pixels here, you know, I think it looks pretty decent. Let's look at what else we got. So this is at Fort Ticonderoga. So I want to get rid of these soldiers. So again, the bricky texture looks okay. And the grass and the ground texture looks okay. But stuff gets filled in the middle of these walls that doesn't look so great. I guess for this one I forgot to add a little bit of extra. So here what's throwing this one off is that I'm trying to figure out where this black thing came from. If you look around the image, that had to have come from somewhere. So for example, probably what it came from is the shadow of one of these cannons up here on the wall. And so what it said was, I found something that looks like brick on the left. What was on the right, it turned out to be cannon shadow, and then other weird stuff kind of started to propagate in. And then definitely something went wrong down here, where again, it was picking up some weird stuff. And so let's look at a big hole. So this is like kind of never going to work. So here, this is like a big building that I'm trying to erase, right? And so, so here, the building is large, right? And so as I chew away along the hillside, you know, things are looking pretty good on the hill, actually, because that's the kind of texture that this algorithm works really well for. But in the middle, you know, I start to build this weirdo, you know, like this fence and this area seems to kind of replicate into this region in a weird way. I just, in some sense, I don't have enough exterior texture to build up something that looks good here. Question?
Yeah, so for the cases which are maybe a little too hard for the computer, but maybe if you had some kind of human intervention to say, okay, this particular assignment work been done, and like it stops every now and then and says, I have trouble here, and then help me.
Yes. Well, actually, one of my grad students did something that was very much like that. So one example, I should have brought it. Well, when we do the chapter with the 3D sensing, I'll do it. So basically, one application of this I thought was really neat, and if I had prepared better, I would show it to you, was when you're doing 3D scanning of objects, you know, stuff that is, so you have a kind of a shadow problem where basically, you know, if I'm 3D scanning, anything behind me is anything that's between the scanner and the wall, like there's going to be a big empty hole of no depth points here. So one thing that I wanted my student to do was basically do inpainting, but with 3D texture instead of 2D colors, right? And so he had a similar thing where it was basically this algorithm applied to 3D, but then there was a point where, exactly what you said, where you say, okay, look, the algorithm self-assesses and says, oh, I don't like this patch. Like, I've got a whole bunch of bad decisions. Instead of putting together a bad patch, which I know will be a big problem, ask the user, and you present the user with a menu of patches that says, okay, you know, this is my best ranking patches. Do you like any of these? The user can click on one, and then the algorithm continues. Or the user can say, no, these all suck. Let's go on to another area and see if we can do better when we come back to this area, right? So that kind of user-guided thing was exactly what I had my student working on. And, you know, I mean, it worked pretty well. If you look back at that paper, we did some statistics of how often the user had to step in for making edits, right? But I will say that, you know, in terms of how often that happens in the literature, I don't think it happens that often. So, and in the implementation, so for example, something like this, we're going to talk more about a different algorithm next time that is really more like what's inside Photoshop right now. But I believe that if you ask Photoshop, fill in this region, it will do so, but it won't give you a chance to intervene, right? Because I think it would be too hard to explain to the average Photoshop user, this is what you should be doing to fix the problem, right? Either it works or it doesn't, more or less. I guess these are just still images of the pictures I showed. Yeah, here, now that this has stopped, you can kind of see all the problems with this inpainted image. You know, the wall looks weird, this region here looks weird, the grass looks weird, and then this lodge. Here you can see what happened is even up in the sky, which you would think would be a fairly easy thing to do, I think what happened was that basically this was a bad choice where maybe there was block boundary that was like just on the border between the sky and the hill. And so maybe what happened was, you know, how can I draw in here? That's so easy to draw. I guess it's just the reader. So I could say maybe over here, right? Maybe there was a boundary, a block like this, and I picked that block out of somewhere over here where it was all sky on the top, and I filled in this hill in the bottom, right? So, and this is actually something I'm going to talk about more next time. So the question of, have I done anything bad by putting this patch in, right? That's a question that a later algorithm that we're going to talk about next week addressed in a much better way. And so kind of as a preview to that, the idea is that you shouldn't be introducing any edges into the image that weren't there before, right? That's kind of like the watchword. You shouldn't be harming the image by putting stuff in there that was never observed, right? And that idea is going to be coming back at us next time, and the kinds of completions that you get from those algorithms look a lot better than this, right? So, so I'd say this algorithm still holds up pretty well for texture synthesis. So if you ever need to inpaint, you know, flowers and grass, this will do great. But for stuff that is larger scale, that's more like what we're going to talk about next time, which are algorithms that the authors claim that you can basically say, okay, I want to take, you know, this image and I want to totally rearrange it, right? I want to put this guy over here and this person over here, and I want to have, you know, this building over there. Retargeting is what we're going to talk about next time. Question?
Is that patch match?
Yes, patch match. So we're going to talk about patch match next time. Yeah, so patch match, you know, the patch match results are really interesting and fun to look at. But that being said, they're not going to work all the time for your images of interest. So, what else do I want to say? So, I guess my final comment is that, you know, people did modify this algorithm in ways that made it smarter. So basically, you know, modifications. You know, one of the most frustrating things about the original algorithm was that you couldn't intervene, and so and there's nothing in the algorithm that really forces things like straight lines to be connected through the hole, right? So the problem is that you could easily get a situation where, you know, say this is the hole, and, you know, you could get something that looked like this at the end, where kind of this didn't line up. Or even worse, something like this, where you got like this, right? That's really bad. Where edges clearly didn't meet up in the middle like they should. And, you know, when you're just taking little patches from here and there, there's absolutely nothing that forces this algorithm to make that happen. So what the modifications proposed was basically to say, okay, you know, let the user have a little bit of input. So the user basically draws this line on the image and says, hey, first I want you to, in a constrained way, fill in patches along this line, right? And so all this stuff gets filled in first, right? And in some sense, that's kind of like, in a way you can think about that like kind of a dynamic programming problem where you've got like this 1D problem of filling in stuff along this thing in an order, right? And maybe there are some other edges, so maybe you fill in all these things first to make sure that all the lines and the junctures in the middle look good. And then you use normal inpainting to fill in the rest of these regions, right? That makes a big difference. So if the strong lines are all continued into the image first and they look good, then the stuff that you're left inpainting is usually not necessarily that hard to do in terms of texture. And so that simple modification made things look pretty good. Another thing is that, you know, like in the lodge example, you know, there may be cases where you don't have just enough other pixels in the image to pick and choose from. And so in that case, there's no reason why you have to only be using this image to grab your patches from. Instead, you could say, okay, this is the image that I want to inpaint inside this hole, and now, you know, you can grab pixels from all these other images in my database that are images of the same type of scene, right? So say I want to inpaint a beach scene or a street scene. Maybe instead of just having to choose windows from the same image, which is often very limiting, you can choose, you know, patches from wherever you want, right? Pull those in. Of course, that makes the whole problem of finding the best patch much, much more burdensome, right? And in some sense, as we'll talk about, you know, next time, the you know, this patch match algorithm we're going to talk about, one of the big innovations, patch match is not really so much of a algorithm for inpainting or retargeting as it is a smart way of making the computational problem tractable, finding the best thing, right? Because you can imagine that you could be searching forever, and you don't want to be doing that. So, okay. So I believe that is it for today. So I'll see you next time.